Okay. So, in the last class we have probably defined what is energy spectral density, what is power spectral density, and we have devised a way to evaluate energy spectral density and power spectral density. So, there was a simple direct way, you directly do the Fourier transform of the signal and then take mod square of that. Okay. You definitely get energy spectral density. Power spectral density, just you have to do a truncation and then do it. Okay. Almost similar method. But the problem with this, let us try to see where we will have problems. So, the first part is, which is the most important part, most of our signals are random in nature. That means the signals will not be deterministic. So, whenever we are doing this Fourier transform, so far whatever we have talked about, it is all deterministic signal. We have exactly defined it over time, that it should be at this particular time it should transit from 0 to 1, then it will remain 1, then it comes to 0 and so on. So, everything was completely deterministic. The entire time means definition of the signal was completely explained. What will generally happen? See, the signals are important mostly for a receiver, because the transmitter, when he is transmitting, suppose I am trying to transmit a voice, my own voice to myself has no information. Okay. It gives me nothing, because I already know I have created that voice. So, that will not give me any extra information. Generally, whenever we transmit signal, the signals are important for the receiver, because receiver does not know what I am going to transmit. So, for him that carries information, and means of course, in this course we will not be doing, but if you read little bit of information theory, you will know that means more uncertainty you have in the signal, more amount of information it is carrying, which is very simply we can state. Suppose in the newspaper every day you see that it is written sun rises in the east. Okay. So, that is almost known information. You do not want that to be in newspaper, because that is something you know. So, will that be a news? That will be a nonsense for you. So, any information which is certainty, or which will eventually occur, and you are aware of that, that will never give you information. But if you say suppose that means IS has bombed in let us say London, okay, that might be very important information for you. Okay. Whether important, not important, it is good, bad, that is a different thing, but that is a information, because you do not see that happening every day. It is very uncertain to you, and that is suddenly happening, and that particular thing will give you some information. So, for a receiver part, whichever way it is, be it from communication perspective, be it from general communication, like I have given that example of newspaper. So, always if you have some amount of uncertainty, or I should say some amount of randomness associated to the signal, then only it carries information. So, therefore, all real signal, if you see it from receiver's perspective, it should be random to him. He should not beforehand know. There is no point in transmitting a sinusoidal to him, because what does he get extra from that? It is just a sinusoidal. If he gets the first period, he knows that it will be just keep on repeating. So, exact pattern of sinusoidal will be known to him. So, there will be no information in just carrying out a sinusoidal. If I just say a pulse train, okay, so let us say it is like this. So, it becomes 1, then 0, and it is a pulse train only. So, it is always 1, then 0, then 1, 0. Is that a information for him? It will never be information for him, because he knows from the first pattern, if he observes, he knows this pattern will be keep on repeating in time afterwards. So, there is no information. He will not be even interested in looking into that. Okay. So, wherever the receiver will be interested, that means the signal that receiver will be interested will be the most realistic signal that we wish to communicate, and those signals from the receiver's perspective will be random. So, if receiver wish to do some processing on that, it must be a random signal which is not expected to him. It should not have any pattern on it. It should not be a deterministic signal for him. So mostly whenever we say we are doing all this signal analysis so far, we have been doing for deterministic signal only for some purpose, of course, because we have to first understand the deterministic signal analysis, then only we will be able to appreciate the random signal analysis. So as long as the signal is deterministic, so far whatever we are doing, but that is not very interesting. Okay. And we know that whatever tools so far we have devised, like let us say Fourier transform. So for a deterministic signal, there is a existence of Fourier transform. We can do Fourier transform, because if you wish to do Fourier transform, the first thing you have to do is you have to take gt e to the power minus j 2 pi f t, but you have to integrate it from minus infinity to plus infinity. That means if you wish to get the gf, you need to know the exact behavior of gt over the entire duration of time from minus infinity to plus infinity. This is absolutely required. So if you wish to do Fourier transform, you need to know the signal completely. Complete definition of signal is required to be there with you. But now we are seeing that most of the realistic signals, suppose receiver wish to know what kind of signal I have, what are the frequency component it has, but unfortunately the receiver doesn't know about the signal pattern. He doesn't, if he knows already the signal pattern, he will not be interested in receiving it, as we have already stated. So if this is the case, then we have a dilemma. Can we now show that for a realistic random signal, okay, which carries some information where I don't know exactly what the pattern will be, so the signal is no longer deterministic to me, can I take that other path of evaluating energy spectral density or power spectral density, and I will still be able to get the spectrum component or spectral density? Can I prove that? Okay, so that will be our next target. So we will just take one example. So very simple example is, generally we transmit, from here we are just now going towards, just to demonstrate it in a easier way, we are just going towards from analog communication to digital communication. Okay. So in digital, you will be knowing that what we do generally, if we have even any digital signal also comes from analog signal. How it comes, I'll tell you. So if you have a signal, suppose let's say this is GT. Let's say this is a voice signal. Okay. So what we generally do, we first sample this signal. Okay. And then we note the amplitude of those signals. Then we also note that what should be the maximum swing of this signal. Okay. So we know the maximum G max or amplitude max that it can go up to if I run the signal for the entire duration, and the G mean of the signal. If we know this range, then we know that the signal, whatever sample we will be taking, those samples will be within this range. Okay. So once I know this range, what I will do, I will divide this entire range into smaller ranges. Okay. As many I wish. Okay. So that's how many I will be defining, that depends on what kind of things I want to design. And then what I do, for each of these samples I want to see which that smaller range it corresponds to, and then for every range I give a equivalent digital representation. Okay. So what happens, suppose I have this length, I subdivide this into, let us say, 256 small ranges. Now this number 256, it is actually 2 to the power 8, right. So basically I know that if I take 8 bits, and if my signals are only binary, it can take only 1 or 0, then with that 8 bit I can actually represent 256 different patterns. Okay. So this is already known to you. So basically 0 0 0 0, all 8 0 will be one pattern, 7 0, last one 1 will be this next pattern, and so on. You can represent up to 256 such pattern. Okay. So then what will happen, wherever this sample stands, I can immediately say, okay, it is in this particular one that has a code book in the binary representation. I will use that code book and I represent that sample with this code book. Like this, every sample I will be able to represent in some binary representation. And if I just put them serially one after another, I will be getting a binary signal stream, which in a way represent this one. And later on, when we will be talking about sampling theorem, PCM, we will see that it actually faithfully represents the signal. So, you can actually from there, from that binary representation, you can actually take out, extract that entire signal, the quality signal. Of course, there will be some noise associated with it. We will also discuss about those things, which is called quantization noise. Right now, we should not be worried about that part. But what we know is that we can, for any signal, we can have equivalent binary representation. Or these days computer communication is very famous. So, in computer communication what happens, every key you press, suppose let us say A, it has a ASCII representation and finally a binary representation again. So, whatever we are generating over there, that also is directly generating some binary streams. So, let us say those binary streams, that is the digital communication actually, I wish to just transmit those binary streams. That means, I will be transmitting either a high signal or whichever way I represent that, a high signal for let us say if it is 1 and a low signal if it is 0, and I do not have to represent any other things. It has some other advantage, we will discuss that later on, why digital communication is better than analog communication. So, right now we are not bothered about that, we just wish to say that okay, this is a valid communication which can also transmit some analog data that is generated, like this voice signal that we have generated. So, it can represent those data also. So, let us say we represent this 1 and 0 in this fashion. So, this is my 0 voltage level, 1 is represented by a pulse like this of duration Tb, where for the first plus Tb by 2 or half duration, it will be having some positive voltage, it can be 5 volt or something like that, okay. And rest of the time it returns back to 0, okay. So, this is called a return to 0 pulse. We will later on, if we have to do line coding, or in digital communication probably we will be doing line coding, then we will be knowing all these things. But right now it is just a representation. So, 1 is represented by this and our corresponding 0 is represented, let us say. So, this is 1 and binary 0 is represented by this. So, it will for first Tb by 2 or half cycle, it will be negative of that same voltage. So, if this was plus V, this will be minus V and rest of the part it will be 0. So, this is my representation of 1 and 0. Now, let us think of a random signal which actually carries information at the receiver. So, that has this binary means random binary streams, that means 1s and 0s are all mixed, it can be 1, it can be 0, I do not have prior information. So, it can be of any way. So, it can be, suppose the first one is 1, then the next one is 1, next one is 0, next one is 1, again another 1, then 1 0. So, it can be of any pattern, you can see that the patterns are broken randomly. Okay. So, it is not a usual pattern, it can be anything. There might be a stream of 5 1s and then followed by 7 zeros, whatever it is, it is all there. Only thing is that anytime you transfer this, there is a statistical property associated with it. Okay. So, whenever we talk about random signal, there should be a statistical property. So, the only statistical property we are just means exerting over here is that it does not have, all these bits does not have any correlation. That means, if this is 1, it does not have any correlation that the next one should be 1 or 0. Okay. So, it can be with equal probability 1 or 0, and also we have equal distribution of 1s and 0. So, that means, if I observe this pulse, it is almost like tossing a coin. If you toss it for enough number of time, you will see probably head and tail number of that frequency relationship, number of heads and number of tails will be almost equivalent. Here also same thing. If I just stretch this pulse up to minus infinity to plus infinity, we will see that as many numbers of 1 will be coming almost similar. So, there is no biasness towards 1 or 0. Okay. So, they are equiprobable with probability half. Right. So, these two statistical property is given for this pulse. So, that means the pulse has a statistical definition or statistical property associated with it, but the pulse is no longer deterministic. It can have any pattern. Okay. So, this is something I know. Now, if I just say, can you evaluate the Fourier transform of this? Not possible, because I do not know, it is a random pulse. I only know about the statistical characteristics, that if this one is 1, I know that the next one with equal probability might be 1, might be 0, but for sure I do not know. And also when this, how these 1s and 0s are arranged, I have no information. So, if I just say, okay, I need to have in the receiver side, I need to know what are the frequency component it has. For that, I need to evaluate the power spectral density of this one. But if I say, okay, give me the power spectral density, you will not be able to evaluate it, because the first stumbling block will be you will not be able to do Fourier transform of this particular signal. So, if you can't do Fourier transform, you cannot even evaluate mod GF square. If this is GT, mod GF square is not evaluatable. Can I now take the other way I have defined to actually get a Fourier means power spectral density of this one? So, this will be our next target. So, for autocorrelation function, what I need to do? Of course, I can see this is a power signal because it stretches from minus infinity to plus infinity. Okay. I'll do truncation and all those things, I'll do that, but it is a power signal, because I'm not saying that this 1s and 0s are up starting from here and it ends over there. I'm just saying, okay, it's a continuous stream of bits which are going on. And see, the time infinity also, you must always argue that why we are doing this, why we are calculating means treating this as a energy power signal, and why we are evaluating power spectral density. You might be always asking, because any signal actually starts at a finite time and it will end at a finite time. No signals are actually, if it is not that the signals the radio waves that are transmitted from Big Bang and it keeps on coming, if that is not the signal. We know all other signals, man generated signals. If you speak, you are not speaking or talking from minus infinity, and you will not be, you cannot even survive up to plus infinity. So, it will never happen, it will always be time bounded. Then it should be all energy signal, and then we should do energy spectral density only. But the counter argument is that the receiver will be seeing the signal for a very small duration, and within that he wished to know, okay, what is the power and all those things. The time duration he is evaluating it, compared to that the signal, the time duration for which the signal lasts is much bigger. So, in that perspective or in that relative sense, we can always say that this is almost like a plus infinity and minus infinity to me, because when I am trying to evaluate the signal, probably compared to that the signal existed much bigger time. So, I can always treat that as if it stretches to minus infinity and plus infinity, and I can treat that as a power signal. So, that is why most of the time you will be actually going towards power spectral density rather than energy spectral density. Okay. So, anyway, those are the motivation why we are doing this. So, now we wish to, so this is a power signal for us. So, all we wish to do is we wish to calculate the time autocorrelation function, right. So, that is our target. So, that means what we have to do, we have to shift this signal little bit slightly, and then we have to multiply it. So, let us say we have shifted by a part tau. Okay. So, what will happen? If as long as this tau is less than this Tb by 2, where Tb is that Tb by 2 is that duration, or Tb is the overall bit duration. So, as long as it is less than or less than equal to this Tb by 2, I know that there will be some overlapping, and each pulse will have same overlap, because it is not going beyond that pulse duration. So, it should be if I just shift by only that tau which is less than TB by 2, it will still have similar overlap at every pulse. So, this pulse also will have similar overlap. So, that is the overlap region, this is the overlap region, and same thing will be happening over here, that is the overlap region, and so on. So, all shifted by tau. Right. Now, let us say, because it is a power signal, I need to truncate it. So, let us say I have truncated it up to t, and I have chosen my, for ease of calculation, I have chosen my t in such a way that some n number of pulses exactly will sit within this. Okay, so, I will get, my t is defined in such a way that I will get exactly, suppose, n number of pulses. Okay, so, I am free to choose any t, there is no problem in that. And we also know as t tends to infinity, this n also will go to infinity, infinite number of bits will be coming. So, infinite number of such pulses will be coming. Okay. So, now my autocorrelation function, the way we have defined it, it should be, because it is a power signal, so it should be limit t tends to infinity 1 by t, okay, and then we have to integrate, right. From minus t by 2 to plus t by 2, and then we will be doing this gt minus tau dt, right. This is what we will be doing. Now, what is my t now? T is n into tb, because there are exactly n number of pulse. So, I can just rewrite this, n tends to infinity 1 by, because t tends to infinity means n tends to infinity, instead of t I can write n tb integration, this goes minus n tb by 2 to plus n tb by 2, and then gt minus tau dt, right. I can write it this way. Now, let us see what is the overlap that we are getting. So, I have already assumed that tau is less than TB by 2, right. So, my overlapping area is, this was TB by 2 minus tau if you take. So, it must be, if the amplitude level is plus 1 and minus 1 taken as that. So, then my overlapping area should be TB by 2 minus tau, right, that is the overlapping area, right, because the amplitude is 1. So, it will be just multiplied by 1, we will get this value only, right. How many such pulses I will be getting? N number of. So, this whole integration I can actually write as n into this area, right. So, I can write limit n tends to infinity 1 by n tb n into tb by 2 minus tau. I can write it this way. So, now what happens? The n gets cancelled. So, my limit is no longer required, because nothing else is there which is putting limit on n. So, therefore, I get this equal to tb by 2 minus tau, and there is 1 by tb, right. Or I can just rearrange it, half 1 minus 2 tau by tb, right. I can write this. So, this becomes my rg tau, okay, which is nothing but a linear function, starts from 0.5 and goes to 0, okay. So, goes to 0 at tb by 2, and because it is a rg tau, we have already proven that it is a even symmetric function. So, it should be exactly like this up to minus tb by 2, that is something we know. So, we can write this rg tau should be half 1 minus 2 mod tau divided by tb, as long as mod tau is less than equal to tb by 2. Good. Up to this we have evaluated, but what about tau can take any value? if now I wish to take tau greater than TB by 2. Okay. So, if I just see this, what will happen? If the tau is greater than TB by 2, this will be shifted beyond this pulse. So, his corresponding pulse will be shifted beyond the corresponding pulse. So, it will now have overlapping with the next pulse, right, or next to next pulse, whatever it is. Whatever happens, it is not his own pulse, it will be next pulse. Now, there is exactly half probability that it will be same. That means 1 will be overlapping with 1 or 0 will be overlapping with 0, okay. Because the 1s and 0s are first of all not correlated and they are equally probable. Okay. So, there is exactly half probability, or I should say 1 by 4 probability that both will be 1, 1 by 4 probability that both will be 0. So, if I just add them, half probability that both will be either 1 or 0. In both cases, the overlapping region gives me positive value, and there is another half probability that they will be actually 1 will be overlapped with 0. So, they will create a negative value, right, or 0 will be overlapped with 1, they will be creating a negative value. So, because there will be infinite number of such pulses, so if I just all those things has to be added. Okay. So, what is happening? Half of them will give me positive value because they are equally likely, half of them will give me exactly same negative value. So, they will get cancelled and I will get 0 all the time. So, this becomes 0 all the time as long as my tau is greater than TB by 2. Is this clear? This is pretty clear because the statistical definition of the signal was already earlier given. Though the signal was not deterministic, but this time autocorrelation I could evaluate because of the statistical definition of the signal already that has been given. So, from there I immediately get a time autocorrelation function which is Rg tau. Now, this is a deterministic signal. Now, I can do Fourier transform. It is very easy. This becomes, because it is a triangular one, it is sinc square. Okay. So, it happens to be this. Okay. Where SGF is actually TB by 4, you can just evaluate that. So, you take this and do a Fourier transform, we will see that it becomes sinc square by FTB divided by 2, and that is the pattern. So, immediately you can see that I had a random pulse which is going to the receiver. Now, receiver has to know the frequency component because accordingly he can design his things, like he wished to put some filter. You might be asking why that filtering is required. There might be other signals also. Okay. So, he has to separate them out. Not only that, even if there are no other signals, you will later on see whenever we will be talking about noise, noise remains everywhere in entire band. If I just do not filter out my signal, then if I put a all pass filter, I will get my signal, that is all right, but I will also get entire noise from entire band, which will be huge noise power, which will actually contaminate my signal. So, I wish to reduce the noise, so then I should put a filter so that out of band noises are suppressed. So, for that reason also I need to know exactly where the signal is existed or which frequency band my signal is existed. So, for that I need to first know, even if the signal is random, I need to know what is the spectral shape of that signal. To know that, for a random signal, I cannot employ the first method of energy or power spectral density. So, I have to employ the second method which we have proven right through. Okay. So, that just tells us that probably the second method is much more important than the first method, because we have already explained that a signal which is important to the receiver must be a random signal, and for random signal it is very difficult to do direct Fourier transform. Rather, autocorrelation, if you know some statistical property, that is pretty much possible. Okay. So, we will end it today's class over here. Next class probably we will start discussing about modulation.